Thank you, Jonathan. So I will be telling you about thawing permafrost. So permafrost is one part of the cryosphere that is on land and actually in the soil. So it's the permanently frozen soil of the Arctic and the Tibetan Plateau and also in Antarctica. And there is a strong feedback effect whereby global warming thaws permafrost, causing release of greenhouse gases that further warms the climate. And this is a problem that is of a very large magnitude, simply because the whole phenomenon of permafrost is of a large magnitude. Permafrost affects about 14 million square kilometers. That's just the whole area of the European Union times 3. And it holds as much carbon as all the vegetation on Earth times 3 as well. So it's a problem of a large magnitude that also responds over long time scales. And essentially what happens is that carbon that has been frozen in the soil for many thousands of years, as it's thawed by climate warming, it starts to be decomposed by microbes that release carbon dioxide or methane as a part of this decomposition process. Next slide, please. This slide illustrates the link between permafrost thaw and the overshoot warming, or the different ways in which we can reach a target temperature. So you see the target temperature on the y-axis, and you have these two different ways of getting there. You have the green scenario where quite rapid emission reductions allow us to just reach the target temperature and then flatten out at, say, 1.5 degrees. And then you have the other option, which is the red line, where we overshoot our target temperature, go above it, and then pull the emissions out of the atmosphere again with negative emission technologies, and then go back down to the target temperature. This is the so-called overshoot scenario. So next slide, please. There are two problems associated with this. First of all, is that the permafrost feedbacks actually cause even higher warming, and they are not accounted for, unfortunately, in the models that are used for COP21 negotiations at this time. And if you press again, the second problem is that the permafrost feedback, they add this additional warming on top of the curves that you see in red or in green shading. But also the permafrost, once it has thawed, there is an irreversibility to it, in that even if we bring the temperatures back down, the thawed permafrost will keep emitting CO2 and methane for several hundred years. So even if we stabilize temperature, permafrost will keep emitting. So avoiding overshoot is critical to avoid this long-term irreversible thaw. Next slide, please. So you can go through these 3 consecutive slides a little bit back and forth. These are basically maps, modeled maps of observed and modeled permafrost thaw that has occurred between the year 2003 and up to 2017. And this is very rapid thaw. Permafrost is usually thought of as a sort of slow giant which responds slowly to climate warming. But in the past few decades, we have seen very rapid responses and rapid thaw, also causing increased emissions from those places where the permafrost is thawing. So next slide, please. And as I mentioned, permafrost emissions are projected to, they are happening now, but they are projected to come a lot more serious by the end of this century. They are slowly growing. And this basically decreases the carbon budget we have available to us to stay under target temperatures. You see these two bar charts here. They show the remaining anthropogenic carbon budget to stay below 1.5 degrees on the left and 2 degrees on the right. And the pink section of these bar graphs is the amount of emissions that the permafrost carbon feedback alone will sort of eat up. So this actually reduces the space we have to actually emit carbon even further. So next slide, please. And the scale of how much of our emissions are sort of eaten up by the permafrost, they depend a lot on how much we overshoot temperatures and how rapidly the climate warms. If we manage to stay at plus 1.5 degrees, then by the end of this century, by 2100, the models that we have project that permafrost alone will emit roughly as much as India today, 2.5 gigatons of carbon CO2 equivalents per year. If we go to 2 degrees, we are approaching the emissions of the EU. And in really high warming scenarios with runaway permafrost thaw, we are looking at permafrost emissions that will come close to almost what China and the US are emitting today. So there's a strong case for limiting emissions that in turn will then keep the permafrost carbon in the ground. Next slide, please. So this final slide, also I want to highlight how the emissions that we trigger today, they will continue for centuries after initial thaw. These bar graphs, the 3 bar graphs on the left, so the blue, yellow, and red ones show the cumulative emissions by 2100 from different warming scenarios, 1.5, 2, and 4. And the much higher bar graphs on the right, those 3 bar graphs actually show us, even if we cap warming by 2100, how much cumulative continued emissions we will have over multiple centuries. This is going up to 2300. So even if we cap warming, the permafrost on human timescales will, for our timescales, it's almost irreversible, and they will keep emitting CO2 and methane that commits many future generations to have to use negative emissions to pull these greenhouse gases back out of the atmosphere. Thank you.